Hello, welcome to the second topic of this class on matrix solvers. This topic is system of linear equations. We will see how a set of linear equations can be expressed in terms of matrix equation, and we will see different operations on the matrices and what are the effects of them on the actual solution vector, rather how the matrices can go through sets of operations without changing the solution much. And as example of this we will consider very simple equation systems, but those are very simple equation systems. We will not spend much time on solving the equation systems, rather we will see the nature of the equation systems. So, we take a two equation, two unknown system, 3x plus 4y is equal to 5, 2x plus 7y is equal to 0. As I said, we are not going to solve this equation, but this equation can be written in a matrix form, where x y is the unknown for which I am seeking the solution. We call this as the solution vector x. The right hand side is another vector b, and the coefficients of the equation is written as a coefficient matrix A. A has a order 2 into 2, x has an order 2 into 1, b has an order 2 into 1. In a general sense, I can write this as A m into n into x n into 1 is equal to b m into 1. And what does that mean? It means that there is a coefficient matrix which has m rows and n columns. X has n columns and the right hand side has m rows. So, right hand side defines what are the number of equations. Therefore, it has m equations and n unknowns. So, you can see a bigger equation system or much larger equation system can be expressed in terms of matrix equation. For example, if I go to a n equation n unknown system, where we will have completely all the equation a complete set of solution, n equation n unknown is there, and this can be represented as a matrix multiplication, where the this is same as the same system of equation, where the coefficients are given as a coefficient matrix A, the unknowns are as the column vector x, and the right hand side is another column vector b. So, equation system can be expressed as a matrix system of unknowns and coefficient matrix using matrix multiplication operations. Now, there can be, like the earlier example what I wrote in the board, is the cases where the number of equation is different than the number of unknowns, and where an example can be A. In this case, A will be A is a rectangular matrix, because the number of unknowns is not equal to the number of equations. So, m is number of equations, n is number of unknowns. So, when we write a m into n, x n into 1, b m into 1, x gives number of unknowns and b gives us number of equations. If they do not match, then A will be rectangular in form. If m is not equal to n, and we can get some of the examples like that. For example, if I have an equation 5x plus 7y plus 2z is equal to 3, and say 2x plus 3y plus z is equal to 0. I will have I can express this as a matrix equation as this can be expressed as 5, 7, 2, 2, 3, 1 and the number of unknown is 3. So, x, y, z, but the number of right hand side column vector, number of elements in right hand side column vector is 2, which is 3 and 0. Similarly, there can be case where number of equations are more than number of unknowns. For example, we can see another case where we have 2x plus 3y is equal to 1, x plus y is equal to 2, and if we add them we get another equation 3x plus 4y is equal to 3, and this can be expressed as 2 3 1 1 3 4 x y is equal to 1 2 3. So, all the cases number of equation is equal to number of unknowns, number of equations is greater than number of unknowns, number of equation is less than number of unknowns, all these cases can be represented in a matrix equation. If we have the ideal case where number of equation is equal to number of unknowns, so that we get a nice solution without spending much equations, extra equations, without solving extra equations, we will have a square coefficient matrix A, otherwise we will have a rectangular coefficient matrix A if number of equations and number of unknowns do not match with each other. So, the next point is what happens if we have a row permutation of the matrix equation, and again for simplicity we will consider the cases with 2 equation, 2 unknown case. This is 3x plus 4y is equal to 5, 2x plus 7y is equal to 0. Now, if we do a row permutation, that means if I write equation, change the order of the equation, say this is equation 1 and this is equation 2. If I renumber the equations as this becomes my new equation 1 and this becomes my new equation 2. If I renumber the equations, we see that the matrix coefficient matrix is row permuted, that is first row comes into the second place and the second row goes to the first place, and same thing happens with the B vector. The first row in the B vector, which is a column vector, goes to the second place and the second row element comes to the first place. So, however, the matrices or the column vectors x y, which are the solution vector remains same. And not only same in value, because we solve the equations we will get the same result, but also same in solution vector remains same. Not only in values, same in order also. So, the permutation is only done in the rows of, or we will write permutation is only done in rows of A and B, not in X. X vector, the vector x remains the solution vector, that remains the same one. So, solving x is equal to b is same as solving the equation a1 x is equal to b1. If a1 b1 and a and b are row permutated form, and the similar row permutation operation is taken place in both A and B matrices. Now, we will see some other row operation, that is we have 3x plus 4y is equal to 0 and we have 2x plus 7y is equal to 0. This is equation 1 and this is equation 2. Now, if I change my equation 2 so that equation 1 is added with equation 2, the solution will be remaining same. So, if I replace this set of equation as 3x plus 4y is equal to 5, which is the original equation 1, and the equation 2 is now equation 1 plus equation 2. The equation system basically gives us similar solution. So, what we write is that the new row, or this is the new row R 2 prime is equal to R 1 plus R 2, and same operation has been taken here. This new row which is R 2 prime of B is equal to or R 1 plus R 2. So, we add rows of A to get a new row and we add rows of B to get another new row, and we see the solution remains same. So, solution which is x and y remains the same. So, row operation in terms of when one row is expressed as linear combination of two or more rows, and this is done in both A and B similarly, the equations remain similar in sense the solution vector x remains same both in terms of its magnitude and in order. We can we can consider a much bigger matrix also, and we will see that the similar methods are existing there. That is, if we have a large matrix with number of rows, and we will see that say elements of row L Lj, which is elements of row L, is expressed as in the new matrix is expressed as alpha into elements of row 1 plus beta into elements of row. We should not choose the wrong, there should not be any mismatch in terms of the operations in the rows of coefficient matrix and B, and then you will end up in this case you are doing one operation in columns in B and another operation in columns one operation in rows of A and another type of operation in rows of B, you will not remain the get the same solution vector. So, matching of the operations is important. So, alpha A I j and then beta A 2 j plus say gamma A L j, and similar operation we do in all coefficients of the all terms of the right hand side matrix B, that is B prime L is equal to alpha B 1 plus beta B 2 plus gamma B L. So, we consider one particular row and do the operations, and we consider another similar row of B and do the operations. And what is the operation? Operation is basically the one elements of all the elements of this row is expressed as linear combination of the elements of the other rows. Linear combination means you multiply the elements of one particular row with some number and add with some scalar and add with elements of the other row multiplied with another scalar. So, multiplied by a scalar and then addition, this is what is said as a linear combination. So, if we can do linear combination of different rows both in A as well as the right hand side vector B, will keep the same solution vector. So, both the cases in the matrices A and A1, B and B1 are linear combinations of rows of A and B can be solved, and the solution vector x will remain same. So, whatever we do with these matrices, if we have Ax is equal to B in an hypothetical case, I find that solving Ax is equal to b is not trivial. So, what I do, forget trivial is not simple, we have to do lot of computing, lot of tricks have to be followed in solving X is equal to b, and A and B and A is not a small matrix, A is a very large matrix. Now, we think of changing this matrix into A1x is equal to B1, doing a row operation, either row permutation or linear combinations of row. Now, the new equation system A1x is equal to B1 is probably easier to solve using our matrix solution algorithm, and we will see when the solution is obtained, the solution of A1x is equal to B1 is exactly same as Ax is equal to B, because these row operations are not doing anything messy with the solution vector x. The solution vector x is remaining the same. So, we go to the next slide, which is column operation. A matrix equation, we have expressed that a matrix equation as a combination of rows, that is the variables multiplied with the coefficients gives us a matrix forms, and each of the coefficient in a particular row is multiplied with all the elements of the solution vector to give one particular element of the right hand side matrix B. Now, you can also see this as a column operation, or a matrix equation can be seen instead of just writing the equations and looking into from the matrix multiplication point of view, we can see a matrix equation as a combination of column, and that is how, if we have this a similar equation 3x plus 4y is equal to minus 1, 2x minus 2x plus y is equal to 1, which is the matrix equation is A x is equal to b. A is 2 into 2, x by x I am now denoting the x which is written in red ink is a column vector x, is not, and it has member x and y. So, this multiplication can also be looked as a factor that the column 3 2, the first column 3 2 is being multiplied by a scalar x, and the second column 4 1 is being multiplied, this is the second column is being multiplied by another scalar x, and when we add this we get, so this is a vector multiplied by a scalar, this is another vector multiplied by a scalar. When we add them we get a resultant vector. So, this matrix equation now can be viewed as a vector equation. We are doing linear combination of vectors and getting resultant vector. So, if in 2D space we can see these two are the vectors 3 2 and 4 1, they are the vectors. Basically 3 2 is 3i plus 2j, 4 1 is 4i plus j, and the resultant vector is 1 1. Now, this if I solve this equation, on solving I will get, probably write it down, on solving, and we can do it by mental maths, we will get x is equal to y is equal to minus 1. That means, I will add a minus of this vector with this particular vector. So, we do this operation, we add this one and we get the resultant vector. So, this equation becomes a vector addition only, and a matrix equation Ax is equal to b can be expressed as finding coefficients x1, x2 up to xn, which can be multiplied with the column vectors to produce a resultant vector b. We can let us go here, sorry. Now, we can look into a bigger matrix equation and we see that similar expression is possible. Let us consider a matrix equation which has number of entries A11, A12, it goes up to A1, and we take a rectangular matrix. that means number of equation is not equal to number of unknown. A21, A22 and it goes up to A2n, and there are many entries in all this case, and the last entry we have to erase this M1, M2 and it goes up to Mn, and this is multiplied with the column vector. Now, I know that there are n columns in A, therefore, x will have n rows from the matrix multiplication, the rule of matrix multiplication. So, this is x1, x2 and it goes up to xn, and the solution, how many elements will the solution vector have, or the right hand side vector have, not the solution vector. The right hand side vector will give us exactly same number of rows that the matrix coefficient matrix is having, because this is the number of equations. So, this will have B1, B2 and it will come up to Bm. So, this is in a sense interesting that the number of columns in coefficient matrix is equal to number of elements in the solution vector, and the number of rows in the coefficient matrix is equal to number of elements in the right hand side vector. So, and we will later see that the right hand side vector is called a member of the column space of coefficient matrix, or it can be expressed, what we will do in the next step is expressing the right hand side vector as linear combination of columns of the coefficient matrix. And the solution vector is this solution vector, this is these are similar entries as the rows of the coefficient matrix. So, solution vector is called a member of the, or it can be shown that it is a member of the row space of the coefficient matrix, that is, if we can have a linear combination of the rows of the coefficient matrix, we can get the solution vector nevertheless. So, now our job is to express this in terms of a vector equation, and what we can write here is that x1 into a11, a21 and it goes up to am1 plus x2 into a12, a22 and it goes up to am2 and it will go on up to xn, which is now a1n, a2n and it will come up to amn, and this is the resultant will be b1, b2 up to bm. So, the matrix equation is now expressed as a vector addition equation, that we are adding number of vectors with unknown coefficients. So, we are adding number of vectors with unknown coefficients, with these are the unknown coefficients to get the resultant, and we have to see what are these coefficients. So, a matrix equation can be expressed as finding coefficients x1, x2, xn, which will be multiplied with column vectors of A and produce the resultant vector, which is B. Now, if we do a column permutation, for example, we have this equation, and if I do a column permutation, that means the columns 4 7 column 4 7 is moved to column 3 2. So, we send this. So, we send this column here in a column permutation, we send column 2 to column 1 and column 1 comes to column 2. So, what happens if we write the expression in a column permuted way, we will see y comes first and x goes later, and the matrix equation becomes 4 7 3 2, which is the column permutation. So, this is A x is equal to b, and this becomes A, say A 1 x 1, because the members of the column vector is also permuted, but the b vector remains same. So, column permutation of A has similar, so this should not be the statement, rather this should be this is not x transpose in x. So, the column permutation is not x transpose, correct it will be x. The column permutation in A is from column 1 and column 2 is permuted, and in x we will see the rows are permuted, 1 will go to 2 and 2 will come to 1. The column permutation is in A is similar to column permutation in B, but no permutation in B. Column permutation in A is similar to permutation in x, but row permutation in x, but there is no permutation in B. So, what we get is A x is equal to B is same as A 1 x 1 is equal to B. A 1 x 1 A 1 and x 1 are similar column and row permutation of A and x. The way the columns of A are permutated, in the same way the rows of x is permutated, and essentially the solution remains same, only the order of the solution matrices, order of the solution vectors changes. Column operation is like linear combinations that can be column operations like linear combinations also can be performed. However, the solution x will change accordingly. What is that? If we see a linear combining of the column, if we see that example, we have a matrix 3 4 2 7, which is multiplied with x and y is giving me solution 5 and 0. So, we can get the equations which is 3x plus 4y is equal to 5, 2x plus 7y is equal to 0. Now, I can assume a new, so this is little more complex, the solution vector will be much changed. We can assume a new solution vector element of a solution vector x prime, which is x plus y, and we can write these equations as 3 x prime plus y is equal to 5 and 2 x prime plus 5 y is equal to 0, which will give me the equation 3 1 2 5 into x prime y is equal to 5 0. Note B is not changed, and the second column, so this is say A and this is A 1. Second column of A 1 is linear combination of columns of A. What is 1 5? We can find it. This is basically this column minus this column 1 5. So, column or the second column, which is 1 5 of A 1, is subtracting the second column first column of A from second column of A, which is we can write C 2 prime, or this is say this is C 2 prime, this is C 1 prime, this is C 1 and this is C 2 is equal to C 2 minus C 1, and x 1 prime is the new x is equal to x 1 plus x 2, or the, so this is, if this is x 1 and this is x 2 and this is x 1 prime and x 2 prime. So, the way the one column is changed in from A to A 1, there will be in a relationship following which the solution vectors will be changed. However, the solution vectors will be a linear combination of the solution of the members of the solution vectors of the previous solution matrix. So, result of row or column operation or combined column operation. The new solution vector is either same as original solution vector, which is for the row operation, the solution vector does not change, or the solution vector is a row permutation of original solution vector, which is for column operation. For column permutation, the solution vector goes to a row permutation or linear combination of elements of original solution vector. So, this is row operation and this is column operation. Therefore, if we do row column operations like interchange the row columns, do permutation, or add row with another row, add a column with a another column, and after multiplying with a scalar, do this type of operations in rows and columns, the solution essentially remains similar. Either it is the same solution, or it is a permutated solution, or it is a linear combination of the original solution vector. So, one very important thing is that how sensitive is the matrix A on row and column operations. That is, this course is focused on matrix solvers. We will discuss about solving the matrix equation, and we will see in certain stages that the matrix solvers perform well for certain properties of the matrices. And if the matrix is diagonally dominant, one of the matrix solver will perform well. That means diagonal entries are larger or equal to the sum of the off diagonal entries. If the matrix is symmetric, one of the matrix solver will perform well in this case. And once we get a matrix which is not diagonally dominant, not symmetric, we can do row and column operation and transform it to the form we are seeking from. So, we have to see what is the sensitivity of matrix A to these operations, what will happen to the solutions, will the solution remain same in row operation, that is the best advantage. In column operation also solution is either permuted or a linear combination of the original solution vector. So, this is a very important thing which is to be checked, and what happens to the property of the matrix, why the solution vector remains essentially same. So, if you look into the matrix, what happens to its properties, so that the solution vector essentially remains same, and this is one very important part of discussion in this course. As the class will progress, we will have more ideas about the properties of A and how they are sensitive to row and column operation. But in the very next class, we will see certain property which is determinant of the matrix, which does not alter much with the row and column operation. There is probably some sign changes in certain cases of row and column operation, and that is a key factor why the solution remains very similar once row and column operation is done. So, today we have discussed up to this, up to the expressing a matrix equation as a system of linear equations and the effect of row and column operations. Next class we will start discussion on determinants. Thank you all.